Cool. Then we proceed with the last talk of the day, which is going to be by Pablo Donato. And the title of the talk is The Flower Calculus, Interactive and Diagrammatic Approach to Constructive Proofs. And Pablo, you can take the stage. Thank you.
Okay, so thanks for having me for this seminar. So I'm going to present a work I did during my PhD thesis, which is called the Flower Calculus, which is a kind of diagrammatic system for building proofs or writing proofs, formal proofs. And so especially in proofs in intuitionistic logic, so constructive proofs. So let me start first with a little bit of context about my research. So I'm really interested, okay, first disclaimer, I'm not going to talk much about category theory in this talk, so sorry for, but there will be some connections to category theory that I will mention at the end. But my research goal more broadly is my research area is interactive theorem proving. And what I'm interested in is trying to design better proof assistants, these systems that should allow us to have a very powerful software environment for doing formal mathematics. And I'm especially interested in making this software more user-friendly, so more accessible to users who have no idea how to code or even very weak background in mathematical logic. So making them very user-friendly. And current interfaces are mostly based on very textual means of representations and symbolic means of representations, which I think is a problem if you want to make them more approachable. So basically the idea in most proof assistants in their interface is that you have a bunch of commands, sometimes called tactics, which allow you to build your proofs by manipulating some symbolic expressions or formulas, which are the statements that you want to prove, okay? So this is a screenshot of some developments in topo theory that I've been doing during my postdoc in the lean proof assistant. Okay, so you see this is just a wall of text and inscrutable symbols. So this is very, very hard to reason on this kind of code. And this is not very approachable. So my idea that I've been developing in my thesis is to have this paradigm that I call proof by action, which is basically a kind of no-code interface for proof assistants based on a graphical user interface where instead of building proofs by typing commands or tactics, you will build proofs by gestural manipulation of formulas. And more specifically, I have developed some various kinds of formalisms that are more diagrammatic. So I want to represent logical statements as diagrams and proofs as direct manipulation of the diagrams. So let me give you an example of a prototype of user interface I've built on this paradigm that I call the flower prover. So first, for a bit of context, I think many of you are familiar with the work of Pavel Sobocinski, and he has done a blog post, very nice blog post about a graphical formalism for linear algebra. And he gives this famous example of how to represent the recipe for crema di mascarpone as these kinds of string diagrams. And so I'm going to take this example, but in a different formalism and more interactive formalism. So this is how it looks like in my interface. So at the bottom, basically the interface is based on these nested boxes. And so at the bottom here, you see the result of my recipe that I want to achieve. So the crema di mascarpone. Then I have my ingredients here in the upper part of that box in this black area. So I have eggs, sugar, and mascarpone. And Yet, so this box is itself embedded in a bigger box, where in the upper part I have a bunch of boxes that represent the different steps that I can apply in my recipe. So the first step would be cracking an egg. So as input in the upper part, I have the egg. And as output in the lower part, I have the yolk and the white. And so what I want to do is apply these steps with the ingredients. So for instance, I can grab this step, okay, and I can copy it here in this area. And now you see that the egg is highlighted in green, so I can apply the step by clicking on the egg. So here, I'm not in linear logic, so I cannot, I mean, I can duplicate my eggs infinitely, so you have to assume that I have infinite supply of ingredients. Okay, so I have applied my, I have cracked my egg, so I can open the box here and I get my two, my yolk and my white. So I can do the same for other steps of the recipe. So I can, for instance, I want to mix the yolk with the sugar and I will get this paste, it's yolk paste. I can stir my whites. Okay, and I can do this for every step. And so you see that with these different actions, I'm step by step constructing the, executing the recipe. So yeah, I can take this one and then the last one. And now finally, I can serve my mascarpone cream to my customers and I can finish my proof. Okay, so that was a nice metaphorical example of how to build proofs in this paradigm through pure direct manipulation of diagrams. And so here I manipulated boxes, but initially I had a different idea for my notation, and I would represent statements rather as flowers. Okay, so this is why the talk is titled "The Flower Calculus." So now I'm going to explain the origin of this calculus, flower calculus, in a formalism called the existential graphs. So this is a diagrammatic proof system, actually a series of diagrammatic proof systems for classical logic that was invented by Charles Sanders Peirce. So it's a very old formalism. It's from the late 19th century. And so you have these three systems that gradually build more expressive logics, starting from propositional classical logic, and then building into first order logic and even higher order and modal logic. So Peirce was really visionary because at this time it wasn't even like a well-known concept, higher order logic. But we're going to focus on propositional logic to make the presentation simpler. So this alpha system of existential graphs is based on three basic icons. So the three basic kinds of diagrams. And the first one is what Peirce calls the sheet of assertion. Okay, so the idea is that if you write something on some space, okay, so here the space will be the slide. So if I write A on my sheet of assertion, then I interpret this as asserting that A is true. So very basic. And if I write nothing, this means that I assert nothing. So this is trivially true. This is the truth constant. Then what I can do is write many things on this space, so through juxtaposition, and I will interpret this as logical conjunction. Okay, so here I assert that both G and H are true. And lastly, I have this construction called the cut. So this should not be confused with the cut from sequent calculus. And the cut is basically, I want to separate some area of the sheet by enclosing it in some curve. And here, to make the idea more iconic, more like the literal meaning of negation is, will be putting the inside of the area in negative. Okay, so this means that G is not true, it is negation. Okay, so we have these three basic constructs, and it is known that in classical propositional logic, you can represent all other connectives with just these basic constructs. So falsity will be just a negation of truth, so this kind of blot. Disjunction will be defined with the usual De Morgan equivalence, so this is not A and not B. And implication with as not A and not B. So this is how these logical connectives look in this notation. And so now that we have a notation for statements, we want a proof system. So we want a bunch of inference rules to build proofs. And so Peirce calls these inference rules, he calls them illustrative transformations. So he has this idea that a proof is a dynamic process of rewriting diagrams. So this is a bit like string diagrams, I believe. And the first, so he has a very limited set of rules. So what I like to see as addition principles, like when you edit text on your computer. So the first principle is a kind of copy-paste principle. So if you have some graph G, and which is next to some graph H on the sheet of assertion, then you can copy G inside of H. Okay. So I will make this more precise with examples afterwards. So there is a converse of iteration, which is called de-iteration. So you can unpaste something that you've pasted earlier. Then there is this insertion principle, which allows you to insert an arbitrary graph G in a negative area, so enclosed in an odd number of negations. And in a positive area, you can do the dual, which is deleting an arbitrary graph G. And then there is a last principle, which is more of a space principle that I like to see it as with some topological intuition. So if you have this kind of ring made of two cuts or two negations, then you can eliminate it or introduce it. It goes in both directions. So, and I like to think of it as a kind of topological deformation. You can collapse the two cuts on themselves or tear up the space to introduce this double cut. So this is really the double negation law in classical logic. Okay, so just an example of proof in this paradigm. So here I start with some graphs that I assume. So you can read it as A and A implies B. And then I'm going to transform it to deduce B, so a kind of modus ponens. So a first step would be to apply the de-iteration rule. So this means that I can erase the white A because it is justified, it already occurs positively as the A here, the black A. Then I can collapse the two cuts. I get A and B, and then I can just forget A to get B, the kind of projection. This is a deletion rule. Okay, so that was the presentation of the system of existential graphs of Peirce for classical propositional logic. And now we want to extend that to intuitionistic logic, which again wasn't even defined or discussed at Peirce's time when he invented the graphs. But still, even if intuitionistic logic didn't exist at his time, he had some intuition about it. And this is a bit startling, but in one of his texts in 1906, Peirce presents this diagram, this kind of diagram that he calls the scroll that is supposed to represent implication. So here, the diagram represents that A and B implies C and D. And yeah, Peirce basically draws it like this. He insists on the fact that it should be a single curve, self-intersecting at a single point. And he doesn't really explain his intuition, but for him, this is really the natural way to represent implication. So, of course, Peirce has a classical interpretation of this. And actually, this makes sense because you can see that as two nested cuts, two nested curves. And so this is like the classical encoding of implication. But here in the notation, I will keep this little orange dot to insist on this idea of a self-intersecting point. Like, in a way, you really need to draw this. You really need to. You can do it in a single stroke of the pen. Like there is this idea of continuity in the representation. Okay. And incidentally, it is Peirce who introduced a dedicated symbol for implication in logic. So I think this is not a very well-known fact, but Peirce is one of the first logicians who really got interested in studying the laws of implication. And in particular, maybe you're familiar with Peirce's law in classical logic. Okay, so we can represent implication, and now fast forward to 2010, Ustra introduced this new diagram, which is a kind of generalization of the scroll, where you can have many inner loops. And so here, this is an example of 5-array scroll with 5 inner loops, B, F, E, D, and C. And so the idea is, so previously we presented disjunction like this on the left and implication like this on the right. And now we want to distinguish between classical implication and disjunction and their intuitionistic counterpart. So they need to have a different representation, different notation. And we will just use this idea of continuity. So basically, if the inner loops are attached to the outer loop, then this is either intuitionistic disjunction in the case where n equals 2, or intuitionistic implication in the case where n equals 1. And you can even have negation defined as usual in intuitionistic logic. When n equals 0, it will just be A implies false, because you can see falsity as the neutral element of disjunction. Okay. And now we finally come to the flower metaphor. So basically, I wasn't quite satisfied with this notation because it reminded me of like a pistol barrel. And so I just had this idea, still with continuity in mind, to turn the in loops, to turn them inside out continuously. And this gives these nice flowers. So now I'm happy. Okay, so let me check the time. Maybe I should hurry up a little bit. How much time do I have left? Okay.
No, I would say you still have at least 5 to 7 minutes.
Okay, so I should definitely hurry up. So yeah, just a little anecdote that in one of his manuscripts, Peirce explains the origin of the word corollary in mathematics. And actually, corollary comes from the idea of a corolla, of like the petals of a flower. And if you think about it in this notation, the corollas or the petals, they can be thought of as corollaries of the pistil, because the pistil implies the disjunction of the petals. So yeah, this is a nice metaphor. So now we are interested in representing quantifiers and variables in order to go to first order logic. And actually, Peirce had a notation for this in his beta system, based on this idea of adding lines between the predicates. And so this is really related to string diagrams. So there is a nice paper from Bonki and other people, that explains how you can see the beta system of Peirce, how you can analyze it in category theory. I think it's related to bicategories and linear bicategories. So yeah, basically the idea is that these lines will represent connections between predicates that share the same variable. So here, okay. So here on the left, I will have P and Q who share the variable X. And on the right also, R and S share the variable X. And how do I interpret, so how do I choose between existential or universal quantifier? This will depend on the polarity of where the line is drawn. So basically, you want to take the outermost point of the line, that is the one which is in the fewer number of cuts. And if it is in a positive area, this will be an existential statement. And if it is in a negative area, it will be a universal statement. And this works because, again, we can have this De Morgan duality. So for X or implies S is the same as there doesn't exist X such that both are and not S. Okay. The problem is in intuitionistic logic, we don't have De Morgan duality. So we need to find another way to interpret these lines of identity to get some quantifier. And the idea is to have a polarity invariant interpretation. So basically, what matters now is not the polarity, but rather whether I am inside of inside loop or outside loop. So if you see it in terms of flower, this means that if I am in a petal, this will be existential, and if I am a pistil, this will be universal. And you see that if I take the negation, the interpretation is the same. Okay, so yeah, known problem of this notation is when you have a lot of in string diagrams, when you have a lot of lines or strings, this can quickly get unreadable. This gives what some people call spaghetti statements. And so actually Quine already had this idea of such a notation, as you can see here in this drawing, but he thought it was too cumbersome. So here, for my purpose of having a nice graphical user interface for proof assistance, I will take a more standard and tractable notation based on variables. So basically, I replace the lines by variables, and the same principle applies. So if I write a variable here in a petal, I will interpret it as existential quantifier, and here in a pistil as universal. Yeah. So I think I might need to skip a lot of slides now because I only have 2 minutes left, maybe. But basically, there are a lot of so the flower calculus is you take this notation and you add a lot of inference rules to have a full proof system. And so basically, the inference rules are an extension of the rules that Peirce had for the existential graphs. So yeah, there is the equivalent of iteration, the iteration. Yeah, I'm not going to get into too much details. You have the equivalent of insertion and deletion, and the idea is that you will basically have twice the number of rules because you need to distinguish between the case where you apply the rule to a petal and the case where you apply it to a pistil or a whole flower. Yeah. Okay, so a bunch of rules. You can have rules to handle quantifiers. So you can instantiate quantifiers with some terms. You have this nice rule for case reasoning. Yeah, I don't have time to explain, unfortunately. But you can also, yeah, okay. And finally, you have a rule to So the idea is that here in this representation of rules, the left-hand side is the conclusion of the rule and the right-hand side is the premise. So you read them from left to right, like from conclusion to premise, because I'm interested in the process of searching for a proof. And so the idea is that if you have an empty petal, then this means that this petal is true, so you can erase the whole flower. And erasing means that I have proved the flower. So a proof will just be a sequence of rewrites that erases a bunch of flowers. Okay. Now, yeah. Maybe I can just mention a little bit of meta-theoretical results. So basically, I have this idea of having two kinds of rules that I call natural and cultural rules. And the interesting fact about this is that the natural rules, they all share some properties. In particular, they are all invertible, which means that if I can rewrite phi into psi, then phi and psi are logically equivalent. So this allows me to do some kind of equational reasoning. And analyticity means that if I have some flower occurring in psi on the right-hand side, it already occurs in phi. So this is similar to the subformula property in sequent calculus. And this allows to reduce the proof search space. And cultural rules, they don't satisfy these properties, basically. And the interesting theorem is that I proved is that, so I proved soundness and completeness for these rules with respect to first order intuitionistic logic by having some Kripke semantics. And interestingly, the completeness works just for the natural fragments of rules. So in the end, composing soundness and completeness, this gives me this admissibility of the cultural rules, which means that I have a complete analytic fragment of the system, which is a kind of cut elimination. And that's it for my talk. So a bunch of related works. And I think the most relevant for your community would be the connection with categorical logic. So there is this nice fact that if you take an arbitrary flower like this, with a bunch of variables and formulas inside it, you can interpret it. I mean, you have to interpret it as this kind of formula, which is exactly the shape of a geometric sequence. So in geometric logic, which has been studied a lot in topo theory. And yeah, I really recommend also the work of Bonki that I already mentioned earlier about this analysis of the beta system of Peirce in Cartesian and linear bicategories. So thanks for your attention. Sorry for the time. And
Thank you for your talk, Pablo. And actually, you were very much in time. And if
okay.
anything, I did steal you a couple of minutes, probably. I think you had a couple of more minutes if you wanted. But okay. So thank you very much for the talk. Let's see if we have questions now. Paul has a question, and also Sylvia has a question. Let's start with Paul.
A simple thing. So I think I saw you talk at the category meeting last year.
Yeah.
I sort of pick up the idea of where the propositions are going in this calculus. I'm not quite sure where the variables are represented, how they are moving around the flowers.
So yeah, I can come back to maybe I should have spent more time. I was too worried about the time, I guess. Yeah, so this is this slide. So basically here you see I've drawn in a pink color the binders. So if you write just a variable in a flower, so either in the pistil or in the petal, you interpret it as a binder, and depending on the location, if it's in a petal, it will be an existential quantifier, and if it's in a pistil, it will be universal. And so in terms of scope, the scope of such a binder will be that in a petal, it will be restricted to things inside the petal. And in a pistil, as you can see here, it will also extend to all the petals of the flower. So yeah, I don't know if you have other questions, if it's not clear enough.
Okay, maybe Paul doesn't know he's muted.
Yeah.
Okay, maybe we take this as an answer to his question and we proceed.
Okay.
Sylvia, do you want to ask a question?
Yeah, thank you. So thank you for your talk. I thought it's very fascinating. So I'm not a mathematician. I work in philosophy of math and on diagrams and proof assistance a little bit. So I'm very curious. And I just wanted to kind of have a more explanatory question about the actual implementation of this graphical calculus. So where are we at? So
So in the prototype I've shown you, basically this interface, it implements the propositional part of the flower calculus. And all the actions are in direct one-to-one mapping to the rules of the calculus. And actually, this idea of having natural rules and cultural rules, which with different properties, it's directly useful in the design of the interface, because I can do my proofs in the natural mode with only reversible and analytic rules. And I have this other mode, which I like a kind of edit mode, where I can apply the cultural rules. So basically the idea is that I can add flowers, new flowers, or new statements that I want to prove by clicking this button. And yeah, and I can also erase flowers that I don't need anymore, so kind of weakening by clicking on this red area. So yeah, basically there is a direct connection between the design of the user interface and the rules on paper. But currently, this is only the propositional part. I haven't had time to implement the quantifiers, but this should
so
work.
you're working just with the extension to create a more complete implementation.
Yeah.
You're still working on that. Okay.
Yeah, still working on that. And the next phase will be to integrate this into a real proof assistant. But yeah, this is still some time, a long time in the future, I think. Yeah.
And so have you been talking with other people who work in the lean proof assistant who are trying to implement different kind of diagrams? So I know some students of Jeremy Avigard, for instance, are interested in this stuff.
I haven't really talked with them. I mean, I introduced myself on the Lean Julep, but I didn't get much feedback. And I contacted Jeremy also, but for other reasons. But yeah, I should definitely reach out to them if they're interested in that.
Yeah, no, thank you. I was just curious. So it's just general questions. Thank you.
Thanks.
Thank you, Sylvia. And now we have another question from another person in the chat. It's Ender. Ender, you can unmute yourself and ask the question.
So thank you so much for your talk. I think that this talk is really incredible and I love intuitionistic logic. So I appreciate this talk and your work on this proof assistant. I actually am not very familiar with proof assistants, however. And so I was wondering if you had any recommendations for proof assistants for classical logic that share similar design goals. I know that you're interested in intuitionistic logic, but are there any proof assistants that you think are for classical logic and would share similar design goals? I know that in your paper, and in your presentation, you linked to Edward Ayers, but do you have any other recommendations?
So there is also work, I can't remember the name. I think it's Linker, who worked a lot on diagrammatic annotations for proofs and integrating them in interactive theorem prover, in a proof assistant. But this is based, so my work is based on the notation of Peirce of existential graphs, and his work is based rather on the more usual notation of Venn diagrams, which is I think a lot more known from people even not familiar with logic. And so I think he has built, I've never tried it actually. I don't know if there is some software that is available online, but I've read some paper where he describes this system, this interactive theorem prover, based on this notation of Venn diagrams. So yeah, that's
Sorry, what is it called? I tried to look it up myself, but I can't find it.
maybe I can send you the link. So it's the name of the author is Linker, Linker. So yeah, but I think if you've read my paper on the flower calculus, I mentioned it in the introduction, so you can find the reference there.
Okay, Ender has reacted with